Welcome back to the deep dive, where today we're peeling back the layers on something absolutely foundational to your car's safety:
Yeah,
semiconductors.
these aren't just, tiny components buried somewhere.
No, they are the literal brains behind all the sophisticated electronic systems that make modern vehicles so smart, so efficient, and crucially, so safe.
That's exactly right. When you consider the incredible technological leaps we've seen in road vehicles, maybe over the last decade or so, everything from advanced driver assistance systems, ADS that
Mhm.
help you stay in your lane, to complex engine controls and, well, the essential safety of airbags, all of it hinges on sophisticated electrical and/or electronic, what we usually call EA2 systems.
Right.
And at the foundational level, the absolute bottom layer of every single one of those systems,
Yeah.
semiconductors, they are, you could say, the unseen heroes.
So, our mission today is to truly understand this intricate world, specifically by diving into ISO 26262.2018, Part 11. This part is fittingly named Guidelines for Semiconductor. We're going to explore precisely why these incredibly tiny, yet unbelievably complex components are so critical for vehicle safety.
Yeah.
We'll also unpack how this particular standard provides unique, tailored guidance for their development, their rigorous production, and even how they're handled when a vehicle eventually reaches the end of its life. It covers the whole life cycle.
And it's good to think of this standard, Part 11 specifically, not as like a rigid rule book, but maybe more like a seasoned chef's guide in a constantly evolving kitchen.
Okay, I like that analogy.
You see, the overall ISO 26262 standard series, it's a specialized adaptation of the broader IEC 61508 series, specifically tailored for the unique high-stakes demands of road vehicles.
Right, the automotive context.
Exactly. And Part 11 provides that crucial bridge. In the rapidly changing landscape of silicon design, a fixed recipe would quickly go stale. It just wouldn't keep up.
Makes sense.
So instead, it offers flexible, expert guidance. It ensures that the chips powering our cars are truly safe by showing engineers how to think about functional safety for silicon, not just giving them a checklist of what to do.
So, what exactly will you, our listeners, uncover with us today? Well, you'll gain a thorough understanding of the unique challenges semiconductors pose when it comes to safety. We'll delve into how faults are defined and meticulously managed at their deepest, most microscopic levels. We'll explore the ingenious safety mechanisms built right into the silicon itself and the rigorous testing and life cycle considerations required to make these components functionally safe.
Yeah, it's a proper deep dive, as you say.
It is, into the very fabric, the very DNA, you could say, of automotive electronic safety. It truly makes you appreciate the unseen work that goes into every drive.
Okay, let's unpack this foundational challenge then. Why are semiconductors, these microscopic marvels, so absolutely critical for automotive safety?
Yeah.
I mean, it seems obvious on one level, but the underlying reasons are, well, fascinatingly complex. Well, as we just touched on, modern road vehicles are overwhelmingly dependent on complex EE systems. I mean, just look around any new car. You'll see features that are entirely driven by electronics, sophisticated braking, precise steering assistance, intelligent engine management, even the split-second deployment of airbags and, occupant detection systems.
It's everywhere.
It really is. These systems are constantly increasing in what the standard calls technological complexity, meaning more powerful processors, more intricate designs, and also in software content, with millions, sometimes billions, of lines of code.
Wow.
What's more, they increasingly involve mechatronic implementation, which is that seamless integration of mechanical and electronic systems. Think of like a smart brake caliper that combines hydraulics with complex electronic control.
So it's not just about adding more electronics, right? It's making them smarter, more deeply integrated, and crucially, taking on increasingly critical roles in actually operating the vehicle. And that trend naturally amplifies the need for incredibly robust functional safety. It's no longer just a nice-to-have feature, but an absolute necessity.
Absolutely.
And that's precisely what ISO 26262 aims to address, adapting that broader IEC 61508 series specifically for our road vehicles.
Precisely. And here's where the unique risks of semiconductors really come into sharp focus. That increasing complexity directly correlates with what the standard identifies as increasing risk from systematic failures and random hardware failures.
Okay.
And critically, semiconductors are at the very bottom, the foundational level, where these risks often originate. They are the tiny building blocks, and if those blocks aren't robust, the entire magnificent structure of the car's electronic system can be compromised, potentially, with severe consequences for safety.
I can absolutely imagine. These tiny components are so intricate, so densely packed with transistors, but technology is evolving at well, breakneck speed. How does that rapid evolution in semiconductor technology impact safety, especially when you're talking about predicting failure rates?
Ah, that's a truly fascinating and frankly challenging point. The standard highlights it explicitly. Semiconductor technology is rapidly evolving, which makes it difficult for published, recognized industry sources for failure rates to keep pace with the state of the art, particularly for deep submicron process technologies.
So the old data doesn't quite cut it anymore.
Pretty much. What this means is that traditional historical failure rate data, maybe collected from older, larger chips, often falls behind the cutting edge of modern chip design. We're talking about transistors measured in nanometers here, often smaller than a virus. Predicting their long-term behavior, especially over the 15-plus year lifespan of a car, is incredibly difficult. So unique and innovative approaches are absolutely needed to assess their safety and predict their behavior. We just can't rely on yesterday's data for tomorrow's technology.
And it's not just about the size, is it? It's also the diverse nature of semiconductor components themselves. They're not all built the same or used in the same way.
Exactly. Semiconductors aren't monolithic single-purpose devices. For safety analysis, they're meticulously considered and partitioned into parts and even subparts.
Okay.
Think of a complex system on chip and Saga inside your car's engine control unit. It's not just one big chip. It's broken down into a CPU, its memory blocks, its communication interfaces, maybe specific accelerators, and so on. Each of those is considered a part.
Right.
And then those can be broken down further into subparts for even finer analysis. This lets engineers focus on the specific safety implications of each tiny functional block.
That makes a lot of sense. Different functions, different risks, even within the same physical piece of silicon.
Absolutely. And these components can be digital, handling your typical binary zeros and ones like the main processor. But they can also be analog or mixed signal, dealing with continuous electrical signals, as you find in, say, a sensor interface, converting the real world into electrical data. Or they could be programmable logic devices, like FPGAs, which are really flexible and can be configured by the user for very specific tasks. And of course, there are the sensors and transducers themselves, which bridge the physical world to the electrical, like an accelerometer measuring G-forces or a pressure sensor in a tire.
And each has its own way of failing, I guess.
Precisely. Each type has distinct characteristics and, crucially, unique fault behaviors that need to be understood and mitigated individually. A fault in an analog-to-digital converter behaves very, very differently from a fault in a memory bit.
And that's why Part 11 isn't a strict rule book then, but more of a guide. As you said earlier, it sounds like that tailored guidance is genuinely crucial here.
It truly is a key distinction. Part 11 is indeed informative and provides possible interpretations rather than rigid, unyielding requirements. It offers guidelines on application of ISO26262 to semiconductors. Now, this might sound less prescriptive, maybe less strong, but in the highly complex and rapidly evolving world of semiconductor development, that flexibility is absolutely crucial. The generalized requirements of the main ISO26262 standard need specific interpretation when applied to the intricate world of silicon development.
So it bridges the gap.
Exactly. It helps bridge that critical gap between high-level system safety objectives, like ensuring that brakes never fail unexpectedly, and the low-level reality of how a tiny transistor in a chip is designed, manufactured, and functions. It helps engineers apply the spirit of safety to the cutting edge of technology.
So it's like a specialized lens, then, allowing us to apply a broad safety framework to an incredibly specific and complex domain without, stifling innovation.
That makes a lot of sense. It sounds like understanding what can go wrong at this microscopic level is really the first critical step.
Yes. Now let's talk about the very language of failure. In the world of functional safety, especially with semiconductors, there's a very specific causal chain that's defined. Faults create errors which can lead to a failure. Can you unpack that for us? What's the precise difference between these three terms? They sound similar.
Yeah, they do, but the distinction is vital. This foundational relationship is absolutely key, and it's defined right in the first part of ISO 26262. Let's use an analogy. Think of it like a house. A fault is a cracked foundation, an unseen underlying physical defect. These are the physical implementation issues within a semiconductor. It could be something like a microscopic broken wire connection, a transistor that's degraded due to age or stress, or maybe a tiny manufacturing imperfection on the silicon wafer. These are the actual physical problems that exist within the hardware, often totally invisible.
So a fault is that physical flaw, the hidden crack. What then is an error? If the fault is the cause.
An error is the deviation from a correct state, and it's caused by that underlying fault. So if you have that cracked foundation, an error might be a crooked floor or maybe a leaky pipe that results directly from that crack. In a chip, if you have a physical stuck-at fault, meaning a specific node in a digital circuit is permanently stuck at a logic 0 or a logic 1, like a light switch welded in place, that physical fault might lead to an incorrect value being stored in a memory register or transmitted across a data bus. That incorrect value is the error.
Got it.
The error is the manifestation of the fault in the circuit's operation. It's the incorrect data or state. It's the first sign something's wrong internally.
And then ultimately that leads to a failure mode.
And then the failure mode is how the component deviates from its specified function, and it's the observable outcome of that error. If our house has the crooked floor and leaky pipes, the failure mode could be, the house actually collapsing, or perhaps just the plumbing failing, making the bathroom unusable.
Right, the functional impact.
Exactly. In the semiconductor world, that incorrect value from the stuck-at fault might lead to a failure mode like wrong program flow execution by the CPU, meaning it jumps to the wrong instruction, or data corruption in a memory block, where values are simply incorrect. Failure modes can be abstract or tailored to a specific implementation, meaning they can be described broadly like output stuck high, or very specifically for a particular pin or function. They represent what the component is doing wrong from its intended behavior, the observable malfunction that could impact safety.
So it's a clear progression. Physical defect, fault, leads to incorrect internal state error, which leads to observable malfunction, failure mode. That clear definition seems crucial. Now let's get into some specific examples of these failure modes across different semiconductor types. Starting with digital components and memories, what kind of issues do we typically see?
Okay, for digital components and memories, we generally categorize faults into two main types, permanent and transient. Permanent faults are pretty intuitive. A stuck-at fault means a node is permanently fixed to a logic 0 or 1, like that light switch welded on or off.
Right.
An open circuit fault is literally a break in a circuit, changing the signal path, kind of like a broken wire inside the chip. A bridging fault is when two signals are unintentionally connected, perhaps due to a tiny manufacturing defect or a whisker of metal, which can lead to unexpected logic results. And then there's the single event hard error, or SE. This is an irreversible change, actual permanent physical damage, caused by a single high-energy radiation event, like a cosmic ray striking the silicon just right and basically burning out a transistor.
Hard error sounds pretty definitive. Ouch. But what about transient faults or soft errors? Those sound, more elusive.
These are fascinating because they're not permanent damage to the hardware itself. They're temporary glitches. A single event transient, or set, for example, is just a momentary voltage spike at a node, often due to a single energetic particle hitting the silicon. It's like a fleeting electrical hiccup. A single event upset, or SCU, is a soft error that causes a single storage location, like 1 bit in memory, to temporarily flip its value, maybe from a 0 to a 1, or vice versa, but without any physical damage. The hardware itself is fine, the data just got temporarily corrupted.
And that can cause problems, even if it's temporary.
Oh, absolutely. And what's particularly challenging are multiple bit upsets, or MBUs. These are 2 or more single event-induced bit errors occurring in the same data unit, perhaps 2 bits flipping in a single memory word due to one particle strike. Simple error correcting codes, or ECC, might be designed to correct a single bit error, but an MBU could overwhelm that capability and lead to an uncorrected error. That's a major safety concern.
So the car's memory might suddenly have bad data without a permanent physical defect, just from a transient event like a cosmic ray? Wow. That's a real challenge. And beyond these general digital faults, memory chips have their own peculiar vulnerabilities, don't they? They're structured differently.
They absolutely do. For memory chips, we have highly specific fault models. For instance, a stuck-open fault describes a tiny transistor switch within a memory cell that gets stuck open, preventing it from ever changing its stored state. Coupling faults occur when the state of one memory cell unintentionally affects or changes the state of an adjacent cell, like neighbors interfering with each other.
Right.
Addressing faults mean the memory system accesses the wrong memory location entirely. And neighborhood pattern-sensitive faults are incredibly complex, where the state of a cell depends on the specific data patterns stored in the surrounding cells. These are notoriously hard to predict and test for.
And how do these underlying physical faults actually manifest functionally? What does it mean for the system if one of these happens? What's a failure mode we'd see?
Right. Functionally, these physical faults and errors can lead to a whole range of critical failure modes that the car system will experience. For instance, a CPU might experience wrong program flow execution, meaning it jumps to an incorrect instruction, potentially leading to completely unintended vehicle behavior. Yeah. You could have data corruption,
Right.
where critical values, say sensor readings or calculations, are simply incorrect, leading to miscalculations, or accessing unintended locations, which could compromise security or simply lead to system crashes. Other examples include deadlock or live lock, where a system gets stuck processing something infinitely, or incorrect instruction execution. The standard actually provides examples like CPU-FM, CPU failure modes, DMOFM, SRAM-RWFM, memory read-write failure modes. These clearly articulate the functional impact, the real-world consequences of these tiny silicon flaws.
Got it. Now, what about analog and mixed signal components? Their failure modes must be a bit different since they're not just dealing with discrete zeros and ones, but, continuous signals.
Precisely. For analog and mixed signal components, failure modes are indeed more nuanced because they involve continuous values, voltages, currents. Instead of simple bit flips, you're looking at signal deviations. For instance, the output might be stuck, high or low, or floating, meaning it's unresponsive or disconnected from the circuit entirely. You could have an offset error where the signal is consistently shifted by a fixed amount, always reading a bit too high or too low. Or a linearity error, where its response isn't proportional to the input like it should be, distorting the signal. For analog to digital or digital to analog converters, ADCs, and DACs, a critical issue is no monotonic conversion curve, meaning the output doesn't steadily increase or decrease as the input changes, leading to completely inaccurate readings.
I can imagine those being much harder to detect sometimes than a simple bit flip in a digital circuit, just slightly off.
They certainly can be. Other common issues include oscillation, which is instability in the circuit causing unwanted continuous variations like feedback squeal, or spikes, which are sudden non-repetitive voltage or current variations glitches. Drift refers to a slow, continuous parameter variation that moves outside the specified range, often due to temperature changes or aging, gradually creeping out of specification over time. For components like oscillators or phase-lock loops, PLLs, which are crucial for timing, you might see incorrect frequency duty cycle, or jitter, which is instability in the timing of the signal. These are all critical for components like power management units, sensor interfaces, or communication transceivers where precise, stable analog signals are absolutely vital for correct operation.
And what about sensors and transducers? They bridge the physical and electrical worlds, so I imagine they have even more unique failure modes tied to their, mechanical nature, right?
They absolutely do. Sensors and transducers are particularly interesting because their manufacturing involves very delicate mechanical procedures, like wafer thinning or wire bonding microscopic wires. These processes can induce mechanical stresses that directly impact performance and introduce unique failure modes, such as a loss of sensitivity where the sensor just doesn't respond as strongly as it should, or a permanent offset in the measurement, meaning a sensor might always read slightly too high or too low, even when nothing is happening.
So literally, the way the chip is physically put together, the stresses involved, can cause a safety issue down the line, affecting its core function.
Yes, that's exactly correct. Furthermore, because many modern sensors are microelectromechanical systems, or MEMS, they're literally miniature mechanical components built right on silicon. Tiny moving parts.
Wow.
This means they are susceptible to physical structure deviations. Their failures can include stiction, where these incredibly tiny moving parts physically get stuck together, like trying to pry apart two wet glass slides. It's like a real physical phenomenon at that scale.
Right.
Or fracture, actual breakage, fatigue over time, delamination, where layers separate, overstress, and creeps, which is a slow, continuous deformation of the material under stress. These mechanical failures can directly lead to incorrect readings or complete sensor failure, impacting critical functions like stability control, braking systems, or airbag deployment, where precise environmental perception is paramount.
This is an incredibly detailed breakdown of how things can go wrong at such a fundamental level. Before we move on, can you quickly explain the classifications of single point fault, SPF, latent fault, LFM, and multiple point fault, MPF? These seem foundational for the safety analysis that follows.
Certainly. These classifications are absolutely critical for the quantitative safety analysis we'll get into. A single point fault, SPF, is a fault that, if it occurs, directly leads to a violation of a safety goal, because there's no safety mechanism or redundancy in place to mitigate it. It's a single point of failure, a direct path to a hazard.
Okay, the most dangerous kind, basically.
In many ways, yes.
Yeah.
Imagine a critical brake sensor wire that, if it breaks, immediately disables the anti-lock braking system with no backup signal path. That broken wire represents an SPF.
Got it. What about latent fault LFM?
A latent fault, LFM, is a fault that exists within the system but remains undetected by any safety mechanism, and whose presence doesn't immediately cause a problem, but when combined with another independent fault, then can lead to a safety goal violation. It's like a hidden threat lurking in the background, waiting for a second failure to create a hazardous situation.
Okay, so it's hidden and needs company to cause trouble.
Exactly. For example, imagine a diagnostic check for a sensor fails, but that failure of the check itself isn't detected. The sensor still works fine for now, but the system thinks the diagnostic is still running. If the sensor then fails later, the system won't know because its monitor is already broken and nobody noticed. That undetected diagnostic path failure is a latent fault.
Okay, that makes sense. And multiple point fault, MPF.
And finally, a multiple point fault, MPF, refers to faults that, in combination with other faults, can violate a safety goal. This is a broader category that includes latent faults, but also faults that might actually be detected by a safety mechanism, but don't immediately cause a safety violation on their own. The key distinction is that it takes more than one specific fault occurring to create the hazardous condition. Understanding these distinctions, SPF, LFM, MPF, is absolutely fundamental to calculating the quantitative safety metrics and designing systems that are robust against these different failure scenarios.
Now that we've decoded how failures manifest, let's talk about quantifying that risk, particularly when it comes to random hardware faults, which is a major focus in functional safety. Part 11 provides specific guidance on this for semiconductors. What are the key metrics here, especially PMHF? That acronym comes up a lot.
Right. The main metric we're usually aiming for is the PMHF, or probabilistic metric, for random hardware failures. It's defined as the maximum probability of the violation of each safety goal at item level due to random hardware failures.
Okay, probability of failure.
Well, yes, but it's incredibly important to understand that the PMHF isn't an absolute reliability prediction in the traditional sense, like predicting exactly how long your light bulb will last. It's primarily used as a design guidance value.
Ah, okay, so not this chip will fail in X hours, but more like
This design meets a certain safety target. It helps engineers compare a new design with existing ones, or demonstrate compliance with the required safety goals for a given ASIL level. It's a target value to engineer towards, ensuring the design achieves a specific, very low probability of contributing to a hazardous event due to random hardware failures.
So it's more about comparative safety and meeting a target rather than forecasting an exact lifespan in the field? And what about the single point fault, SPF, and latent fault, LFM metrics we just discussed? How do they factor into this quantitative picture?
The single point fault, SPF metric, and the latent fault metric, LFM, are derived from the base failure rates of the individual components, and crucially, the effectiveness, the diagnostic coverages of the safety mechanisms we build in to detect or control those faults.
Right.
They are crucial for assessing how effective those safety mechanisms actually are at mitigating the random hardware faults. A high SPF metric means there are too many potential single points of failure in the design that aren't adequately covered by safety mechanisms. A high LFM metric means there are too many undetected faults, potentially lurking in the background, that could combine with other faults later to create a hazardous situation. These metrics essentially guide engineers to find and eliminate those critical vulnerabilities.
Given how rapidly semiconductor technology evolves, estimating those base failure rates must be incredibly challenging, as you mentioned. How does Part 11 guide developers through that, especially for these cutting-edge chips?
It is a significant challenge. The standard reiterates that the fast pace of deep submicron process technologies makes traditional published failure rate data incredibly difficult to apply directly. Reliability handbooks, often struggle to keep pace with the state of the art, particularly for these advanced nodes where quantum effects can even start to play a role. We're truly pushing the boundaries of physics sometimes, which makes predicting failure based purely on historical data a very complex task.
And there's also that critical distinction between systematic and random failures in ISO26262, right? This seems fundamental to how you approach reliability calculations for safety.
This distinction is absolutely crucial. ISO26262 explicitly makes a distinction between systematic and random failures. Most general reliability estimates you might find out there, they often don't make this differentiation clearly. They tend to lump everything together.
And that's a problem because
It can lead to excessively conservative results for safety analysis by including systematic failures, which are really errors in design or process that ideally should affect every single chip, rather than focusing just on the random degradation or failure in individual components over time. ISO26262's metrics, specifically PMHF, SPF, and LFM, focus only on random hardware failures. This precise focus allows for more accurate and relevant safety assessments of the hardware design itself. Systematic faults are tackled through different, rigorous development processes, not through these probabilistic metrics.
I see. So you're not trying to quantify, say, a human design error in the same way you quantify a transistor randomly failing due to wear and tear after years of use. Okay, what about the classic bathtub curve of failure rates? Is that still relevant for semiconductors, and how do you handle rates that might not be constant over time?
The bathtub curve, which depicts that early life period of infant mortality, then a long useful life with a roughly constant failure rate, and finally a wear-out phase with increasing failures, is often used as a simplification. And while the useful life phase is often assumed to have a constant failure rate for calculations, real semiconductor failure rates might not be perfectly constant throughout their entire lifespan. The standard acknowledges this reality. It states that methods exist to simplify non-constant failure rate distributions by using approximations of constant failure rate.
How do they do that?
Well, perhaps by taking the maximum failure rate observed over a specific period, or by defining the product's required operating lifespan carefully to stay within the region where the constant rate assumption holds reasonably true. This allows the use of the standard quantitative metrics, while still acknowledging the complex reality of how failure rates might actually behave in the field over many years.
And what specific techniques and sources do developers actually use to estimate these base failure rates for semiconductors, especially with all these complexities we've discussed? Where does the data come from?
There are several established methods, often used in combination. One primary approach is experimental testing, which includes really rigorous stress tests like high-temperature operational life or HTOL testing.
Right, the burn-in type stuff.
Exactly. Chips are operated at extreme high temperatures and voltages for extended periods, hundreds, maybe thousands of hours, to accelerate aging and reveal latent defects that might cause failures later. There's also specific soft error testing for radiation sources, often guided by industry standards like JEDEC JEST 89A, which involves bombarding chips with radiation to simulate cosmic rays and test for transient faults, like SEUs and MBUs.
Okay, so direct testing. What else?
Another valuable, though often difficult source is the observation of field incidents. This involves meticulously analyzing components returned from the field, like chips from a vehicle involved in an incident or warranty claim, to understand how and why they failed in the real world.
That must be hard to get reliable data from.
It is. As the standard notes, distinguishing purely random hardware failures from systematic design issues or even system-level problems in field data can be tricky and requires deep expertise. And finally, industry reliability data books such as the FIDE's Guide, SNDA 879-500 or IEC 61709 are commonly used as a starting point. These provide reference failure rates based on historical data, which are then often adjusted with engineering judgment for the specific application, the component type, the manufacturing technology node, temperature profiles, and so on. It's really a combination of prediction based on models, observation from the field, and rigorous experimental testing.
That's a lot of data and methodology just to estimate how often a microscopic component might fail randomly. But even with all that, you still need clever ways to prevent these faults from causing harm, or at least detect them. Let's delve into some of the ingenious safety mechanisms built directly into semiconductor designs. Starting with digital components and memories, what are some of the watchdogs of data integrity?
Absolutely. For digital components and memories, some of the most common and effective mechanisms are all about safeguarding data integrity and ensuring correct operation, even if a fault occurs. Error detection correction codes, or ECC, are prime examples.
ECC, yeah, I've heard of that.
Right. ECC, like the common SEC single error, correct dual error detect, adds redundant bits, parity bits essentially, to every memory word. This allows the system to not only detect bit failures, but in many cases, automatically correct single-bit errors on the fly. It essentially self-heals the data before it can cause a problem.
Yeah.
Some advanced ECC can even detect certain addressing failures if designed cleverly, which is crucial for the reliability of memory-intensive systems.
So it's like adding a self-healing layer to the memory, correcting mistakes before they become a bigger issue. What else helps guard the data?
You also have cyclic redundancy check, or CRC, which is often combined with something called a memory signature. This involves mathematically compressing large blocks of memory data into a small digital signature, or checksum. Later, perhaps during operation or at startup, this signature is recomputed from the current data and compared to the stored one. If they don't match, it detects that the data has been corrupted. Think of it like a digital fingerprint for a block of data. If the fingerprint doesn't match, you know the data has been altered somehow.
Clutter.
Block replication is another straightforward, though more resource-intensive, method. You simply duplicate critical memory space and perhaps the associated logic that uses it. Both copies run in parallel, and their outputs are constantly compared. If they ever mismatch, you immediately know there's an error in one of them.
And specific tests for memory that aren't just about detecting errors that happen passively, but actively looking for potential faults.
Yes, exactly. Like the RAM March test. This isn't just a general check. It involves writing and verifying specific, complex patterns, like walking ones adheras through the memory array, to detect persistent bit failures, stuck at faults, bit transition issues where a cell can't flip from 0 to 1 or vice versa, addressing faults, and even those tricky linked cell failures or coupling faults where one cell state impacts another. It's a very thorough diagnostic, often run at startup or periodically.
Okay.
A simpler but much less comprehensive mechanism is the basic parity bit, which adds just one extra bit to a data word to make the total number of ones either always even or always odd. It's a quick check that can detect any single corrupted bit or any odd number of corrupted bits, but it doesn't offer any correction, and crucially, it won't catch an even number of errors, like 2 bits flipping simultaneously.
And for the CPU itself, the brain of the operation, what about something like dual-core lockstep? That sounds like a really powerful way to ensure the processor is always doing exactly what it should.
Dual-core lockstep is indeed a very powerful and widely used technique, especially for high ASIL CPUs. Here, 2 identical CPU cores run in parallel, executing the exact same instruction stream, often synchronized clock cycle by clock cycle.
Okay.
A dedicated hardware comparator module continuously checks their outputs, bus signals, register writes, everything. If there's any mismatch between the 2 cores, even for a single clock cycle, an error is immediately detected and flagged.
Wow, instant detection.
Yeah, it's like having 2 identical drivers at the wheel, constantly verifying each other's every single move in real time. This provides very high diagnostic coverage against random hardware faults occurring within the CPU core itself, making it incredibly reliable for safety-critical functions like engine control or steering assistance.
Switching gears a bit to analog and mixed signal components, what are some of the sentinels of signals in that domain, guarding against deviations in those continuous values?
Right. For analog and mixed signal, it's less about bit flips and more about monitoring continuous values and ensuring stability and accuracy. Over and under voltage monitoring is a common one. It constantly compares a regulated voltage, say the power supply for a critical block, to specified upper and lower limits. If the voltage drifts out of that safe range, it triggers an alert or even a shutdown, much like a hospital monitor watching a vital sign.
Makes sense.
Similarly, current limiting and overcurrent monitoring prevent the current flowing through a circuit from exceeding safe levels. This protects output devices like transistors from burning out and prevents potentially damaging electrical overstress conditions.
Are there watchdog timers in the analog world too? Something to make sure active components like oscillators are still, oscillating?
Yes, conceptually similar. There's an analog watchdog that monitors the proper operation of an oscillator or another periodic signal. It typically uses a special circuit called a monostable, which is like a timer that needs to be regularly kicked or re-triggered by the signal it's monitoring to stay in its normal state. If the monitored signal stops or goes out of frequency, the watchdog doesn't get kicked, its timer expires, and it signals a fault. Yeah. We also have thermal monitors, which are basically on-chip thermometers. They detect when a circuit's temperature exceeds a predefined safe limit, allowing the system to take action, maybe by reducing performance or shutting down to prevent overheating and potential damage or unreliable operation. And for self-testing, analog built-in self-test, or BS, involves designing a circuitry that can exercise diagnostic paths by injecting specific currents or voltages. This ensures that the monitoring circuits themselves can correctly switch between detecting faulted and non-faulted states, verifying their proper operation without needing complex external test equipment.
What about programmable logic devices, like FPGAs? How do they protect themselves, given that their internal logic is configurable, almost like software on silicon?
That's a great point. PLDs, being configurable, have unique mechanisms focused on ensuring their programmed logic is intact and hasn't been corrupted. Configuration readback is crucial here. The device can literally read back the contents of its configuration memory cells, the bits that define the logic functions and interconnections, and compare them against the intended design values may be stored elsewhere or recalculated.
So it checks its own programming.
Exactly. If there's a mismatch, it signals an error. This could be due to a transient radiation event flipping a configuration bit, an SEU in the configuration memory, or perhaps more permanent memory error. Separate voltage planes can also be used within the PLD fabric to prevent shared power supply issues from affecting independent safety functions, electrically isolating critical parts from non-critical ones. And PLDs can cleverly use a mix of spatial and temporal redundancy, leveraging their inherent reconfiguration capabilities to implement safety measures. For example, they might have duplicate logic blocks, spatial, or dynamically remap logic around a detected faulty area, temporal, effectively working around a problem on the fly.
And finally, sensors and transducers. They're perceiving the physical world. How do they safeguard themselves, often having to deal with both electrical and, as you mentioned, mechanical aspects?
This is where it gets particularly interesting, I think, because some safety mechanisms are not purely electrical. They're physical or mechanical. For MEMS accelerometers, for example, a sealed-proof mass filter involves designing a sealed chamber around the tiny moving mass with a specific gas pressure inside. This pressure dampens the movement, filtering out high-frequency vibrations or noise from the environment that could cause false readings.
Clever.
For MEMS pressure sensors, redundant diaphragms are sometimes used. This involves having a second, non-moving reference diaphragm built right next to the primary sensing diaphragm. Comparing the signals from both allows the system to detect drift or failure in the primary sensor. There are also various transducer-specific self-tests designed to verify the integrity of the entire signal path, from the physical sensing element right through to the electrical output.
And you mentioned something really fascinating earlier about non-electrical safety mechanisms, almost like physical safeguards built into the MEMS structure itself.
Yes. This is one of the most unique aspects detailed in Part 11, MEMS-specific non-E safety mechanisms. These are physical, mechanical, or even optical mechanisms designed within the transducer structure itself that can directly detect certain types of failures and help the transducer enter a safe state, even without relying on an electrical detection circuit.
Like what, for example?
Think of a simple physical stopper, a tiny barrier designed to prevent excessive movement of a micromechanical part if, say, a spring fails. Or imagine a tiny floating cantilevered finger that, if the main structure breaks, physically moves into a position that blocks a light path or makes electrical contact, directly indicating a structural failure. This provides inherent coverage against certain random and even systematic faults at the most fundamental physical level of the sensor. It's truly building safety in from the ground up in a very tangible, mechanical way. It's a testament to how comprehensive safety design needs to be for these critical components.
So we've talked about how faults are categorized and some of the clever ways designers try to mitigate them with safety mechanisms. But how do you actually analyze and quantify these weaknesses systematically? That's where failure mode effects and diagnostic analysis, or FMIDA, comes in, which Clause 9 details specifically for semiconductors. What's its power at this semiconductor level?
Right. The FMEDA is a crucial, really systematic step. Its purpose is to identify its failure modes, evaluate their impact on safety goals, and calculate their diagnostic coverage. It's the core quantitative safety analysis that ties everything together, allowing engineers to actually put numbers to the residual risk after considering the failure rates and the safety mechanisms.
And while FMEDA is used at higher system levels too, applying it rigorously to semiconductors must allow for incredible precision, right?
It does. It allows you to get right down to the nitty-gritty. The analysis can, and often does, extend down to the subpart or elementary subpart level for greater accuracy, especially during the early development stage of the silicon design itself.
Subpart level. You mean breaking the chip down into really small blocks?
Exactly. This is vital because different tiny functional blocks within a complex chip, think of a specific CPU pipeline stage, a memory controller's arbiter, or a particular peripheral interface, will have different inherent failure rates based on their complexity and size, and crucially, different potential impacts on safety if they fail. By breaking it down like this, you gain a very precise understanding of individual risk contributions from each tiny piece.
And how is the base failure rate for a whole component, say a memory controller, distributed across all those different possible failure modes you mentioned earlier, stuck at, open, etc.?
Yeah, that's a key part of the FMETA.
Yeah.
The estimated base failure rate for a component or subpart is distributed across its potential failure modes. This distribution is critical because, as we discussed, different safety mechanisms are designed to cover different failure modes with varying levels of effectiveness.
Right, ECC fixes bit flips, but not power failures.
Exactly. An ECC mechanism might cover certain bit flip failure modes in memory very well, giving high diagnostic coverage for those, but it won't protect against, say, a power supply fluctuation affecting the whole chip. For analog components, this distribution might initially be assumed as uniform across different failure behaviors, like stuck high, stuck low, offset error, or it can be later refined based on detailed circuit analysis or simulation, identifying which parts of the circuit are most likely to cause which failure mode, allowing for more targeted safety mechanisms or analysis.
And then there's diagnostic coverage, or DC. This sounds like it's just a percentage of how well a particular safety mechanism works for a specific fault.
Yes, diagnostic coverage, or DC, is precisely that. It represents the percentage of dangerous failures, those potentially violating a safety goal, associated with a specific failure mode that a particular safety mechanism is expected to detect or control.
So higher DC is better.
Absolutely. For example, an advanced ECC might claim a high DC for single-bit errors, maybe 99% or even higher, whereas a simple parity bit might have a much lower DC, say 50%, for random bit flips, because it can only detect an odd number of errors and offers no correction. Crucially, the claimed diagnostic coverage for any safety mechanism must always be supported by robust evidence. It can't just be a guess.
Evidence like what?
Evidence typically comes from extensive simulations, formal verification, fault ingestion campaigns, which we'll get to, and characterization testing on actual silicon samples. It's not just a theoretical number, it has to be proven and justified.
What's particularly fascinating here, I think, is the concept of safe faults that you mentioned briefly before. Does that mean not all faults are equally bad, or maybe even bad at all from a safety perspective? It seems a bit counterintuitive to call any fault safe.
It does sound a bit strange at first, but it's a very important distinction in the standard. Not all faults necessarily lead to a violation of a safety goal. A safe fault is formally defined as one that will not contribute to the violation of a safety requirement, either because the fault affects a non-safety relevant part of the chip or because its effect is benign.
Okay.
This is particularly relevant and interesting for analog components, because analog signals operate in continuous ranges and usually have inherent tolerances, meaning they can deviate slightly without losing their intended function. A parametric failure or drift, say a voltage that drifts slightly off its nominal value but remains within the specified functional tolerance range, can actually be classified as a safe fault. It's an imperfection, yes, but not a dangerous one in that context.
So an analog component has an inherent capability to tolerate a fault up to a certain point, almost like a flexible bridge that can sway a bit in the wind without actually collapsing.
Yes, that's a great analogy. Exactly. This concept directly impacts the hardware safety metrics, SPF, LFM, PMHF. These safe faults do still contribute to the overall failure rate of the component. There are still faults occurring in the silicon, contributing to the denominator in the metric calculations. However, they don't contribute to the numerator, the part representing failures that violate safety goals. It's about rigorously distinguishing faults that actually matter for safety from those that are merely performance deviations or affect non-critical functions, but don't compromise the required safety function. For instance, if a voltage regulator for a non-critical part of a digital circuit experiences a failure that only causes its output voltage to fluctuate slightly, but still keeps the voltage within the acceptable thresholds for the digital logic it supplies, that might be classified as a safe fault.
Okay, that clarifies it. Now, even with all these meticulous analyses of individual faults and safety mechanisms, complex systems often have hidden interdependencies. Things that look separate aren't always. That brings us to the dependent failure analysis, or DFA. Why is DFA so essential, especially at the semiconductor level? What's it trying to uncover that FMETA might miss?
Right. Even the most robust individual safety mechanisms designed to cover specific faults can be completely undermined by common root causes or unexpected cascading effects. DFA is the process specifically designed to identify these possible common cause and cascading failures between elements that are supposed to be independent according to the safety architecture.
So checking if your redundant parts are truly independent.
Precisely. It's about ensuring that requirements for freedom from interference and independence are truly met in the physical implementation. Without a thorough DFA, you might miss a single point of failure, like a shared power rail or clock signal, that affects multiple independent safety mechanisms simultaneously, rendering them all useless at the same critical moment and exposing the system to unexpected hazards. It's about uncovering those hidden single points of failure that aren't obvious just by looking at block diagrams.
And is DFA quantitative, like F-meta, giving you hard numbers for the probability of dependent failures? Or is it a different kind of analysis?
No, importantly, DFA is primarily performed on a qualitative basis. The standard explicitly states that no general and sufficiently reliable method exists for quantifying such failures with high confidence.
Why is that?
Because the potential causes and coupling mechanisms are just too diverse and complex to model accurately with probabilities. So DFA relies heavily on expert judgment, structured analysis methods like checklists and brainstorming based on potential initiators, and robust design practices rather than trying to calculate precise statistical numbers. It's about identifying how things could go wrong in a dependent way, tracing those potential chain reactions. It's, you could say, more like detective work than a statistician's task.
What are some examples of these dependent failure initiators, or DFIs as the standard calls them? Where do these common root causes typically come from within a complex chip?
DFIs can come from various sources right there on the silicon. You have shared resources, which are obvious candidates. Things like a single clock generation circuit, PLL, that provides timing signals for multiple functions, embedded voltage regulators that power different sections of the chip, direct memory access, DMA controllers that interact with multiple peripherals and memory, or even shared test logic infrastructure. If that shared clock fails erratically, for example, it could instantly undermine the timing and coordination of several otherwise independent functional elements, potentially leading to a system-wide failure.
Okay, shared resources make sense. What else?
Then there are random physical root causes that can spread. These are often localized defects that can propagate or have wider effects. This includes a microscopic short circuit in one area, creating noise or heat, or particularly nasty phenomena like latch-up, where a parasitic SCR, silicon-controlled rectifier, structure accidentally formed in the silicon can trigger, causing a high, uncontrolled current flow, essentially short-circuiting parts of the chip and leading to widespread malfunction or even permanent damage. Other examples include crosstalk between adjacent signal lines, or local heating, caused perhaps by a defective internal voltage regulator where the heat spreads and affects the performance or reliability of nearby components.
And systematic issues too, like design flaws.
Absolutely. Systematic faults are major DFIs. These include design errors that might be replicated across the chip if a block is reused, manufacturing flaws like mask misalignment affecting multiple components simultaneously, or environmental factors that affect the whole chip, such as unexpected temperature extremes, both hot and cold, electromagnetic interference, EMI, or physical vibration and shock. A single design flaw in a commonly used digital library cell, for instance, could propagate throughout multiple instances of that cell, creating a common vulnerability across the chip.
How do these DFIs actually induce a disturbance? What are the coupling mechanisms that allow a fault or disturbance to spread from one place to another?
A coupling mechanism describes how a root cause creates a disturbance and how that disturbance travels or spreads. The standard identifies several types. It could be conductive coupling, which is a direct electrical contact through a wire, a shared power or ground line, or even the silicon substrate itself. Or it could be near-field coupling, which is inductive magnetic field or capacitive electric field, coupling over very short distances, like signals unintentionally jumping between adjacent metal traces on the silicon die. And then there's radiative coupling, where electromagnetic waves travel over a longer distance, essentially acting like miniature antennas and receivers within the chip or package, especially at high frequencies.
And these disturbances can travel through various propagation mediums within the chip, almost like a silent infection spreading through the system's veins and arteries.
Yes, exactly. They can spread through signal lines, the intricate clock distribution network, the power supply network, the underlying silicon substrate itself, which isn't a perfect insulator, the chip's package, and even the surrounding air for radiative effects between chips or components. The DFA also considers locality. Does the disturbance affect multiple elements simultaneously or just one, potentially leading to cascading effects? And timing, such as propagation delays or the periodicity of the disturbance, is it constant noise or intermittent? Understanding these potential paths is absolutely crucial to building effective barriers and proving independence.
So, given all these potential ways things can go wrong dependently, what are some of the mitigation strategies engineers use to prevent or control these dependent failures from becoming catastrophic? How do you build those barriers?
The strategies are varied and absolutely crucial for demonstrating sufficient independence, especially for higher ACell systems. They often involve a combination of approaches. One key strategy is dedicated independent monitoring of shared resources. For example, having a completely separate simple watchdog monitoring the main complex clock signal, or having independent voltage monitors for critical power rails that aren't susceptible to the same failure modes as the main regulator. We also use techniques for diversification of impact.
Diversification, like what?
This can mean things like introducing a small, deliberate clock delay between the master and checker cores in a lockstep system so they aren't perfectly synchronized, possibly making them less susceptible to simultaneous upsets from a single transient event. Or using genuinely diverse core designs, maybe different architectures or synthesized differently, for redundant channels. Or ensuring redundant blocks use different physical routing paths on the chip so a single localized defect is less likely to affect both. It's about making sure redundant elements aren't identical in every single respect.
Okay, so making them different enough? What about physical separation?
Yes, physical separation isolation measures are very common on the silicon itself. This includes using guard rings, specialized diffusion regions, to isolate sensitive analog blocks from noisy digital sections, placing critical redundant blocks in separate power or substrate wells, ensuring sufficient physical distance between them, or strategically placing on-chip heat sinks or spreading heat efficiently to prevent thermal coupling. It's like building firewalls on the chip.
Just good design practices.
Absolutely. Robust design principles are fundamental. This means using conservative design margins, designing circuits to be inherently less sensitive to noise or voltage variations, maybe implementing adaptive measures like dynamically reducing clock frequency or voltage if overheating is detected. And fundamentally, the entire process relies on continuous compliance to ISO26262 series of standards throughout the design and manufacturing process. Rigorous reviews, verification, and configuration management all help avoid introducing these common-cause systematic failures in the first place. This detailed dependent failure analysis, even though it's primarily qualitative, is absolutely critical for understanding and shoring up the chip's vulnerabilities against these insidious hidden failure modes.
Moving on to Clause 10, stress testing safety, specifically through fault injection. This sounds like a very proactive approach, deliberately trying to break things. Why is this methodology so imperative for semiconductors in particular?
Fault injection is a well-known methodology, and it's incredibly powerful because it directly simulates the occurrence of faults to assess the effectiveness of the safety mechanisms designed to handle them. For incredibly complex digital circuits, as we touched on, it's often impractical or even impossible to exhaustively test the effects of things like single-event upsets, SEUs, at the actual hardware level. You just can't reliably take a laser or a particle beam and precisely flip one specific bit inside a multi-billion transistor chip running at gigahertz speeds to see what happens in every possible state.
Right, the scale is just too small and fast.
Exactly. So simulation-based fault injection becomes absolutely key here. It allows engineers to simulate potentially millions or even billions of fault scenarios across the entire design space, different fault types, different locations, different times in a controlled software environment. This achieves a level of coverage that would be utterly impossible or prohibitively expensive to attempt solely with physical hardware testing.
So it's about proactively breaking the chip, or at least simulating breaking it in very specific ways, to see exactly how it reacts and, crucially, if its safety mechanisms kick in exactly as expected.
That's precisely it. Its key purposes are manifold. It directly supports the evaluation of the hardware architectural metrics, like the SPF and LFM metrics we discussed, by injecting faults and seeing if they are detected, covered by a safety mechanism, or if they are safe, or if they lead to a potential safety goal violation. You can quantitatively calculate those metrics.
Okay.
It helps evaluate the diagnostic coverage, DC, of a specific safety mechanism by literally injecting faults that the mechanism is supposed to detect and verifying that it actually does under realistic operating conditions. It's absolutely crucial for the pre-silicon verification of a safety mechanism, confirming before you manufacture the chip that the safety mechanism meets its requirements and can properly control a fault's effect, triggering the intended fault reaction, like signaling an error or entering a safe state.
And finding weird edge cases, too.
Yes, it's great for verifying specific, hard-to-reproduce corner cases, those rare combinations of operating conditions and fault occurrences that might only happen once in a blue moon, but could be critical. It's also used for checking interconnectivity during the integration of various IP blocks, pre-designed functional units, within a larger system on chip, ensuring that faults injected in one block don't propagate unexpectedly or incorrectly affect other blocks.
How is fault injection actually performed? What are the practical steps in setting up such a simulation campaign?
It can be done at various abstraction levels of the design representation. You can inject faults into high-level behavioral models, like in C++ or System C, early in the design process to get a quick overview of the system's response to major functional block failures. Or, more commonly for detail verification, you go down to the gate-level netlist, which is the very detailed description of all the individual logic gates and their connections, or perhaps at the RTL register transfer level, which describes the flow of data between registers using languages like Verilog or VHDL.
And the level you choose depends on.
The choice of abstraction level depends on the specific fault model you're trying to inject. Some faults are only meaningful at lower levels. The feasibility and speed of the simulation, given its complexity, gate level is much slower than RTL, how observable the effects of the fault are at that level, and the desired accuracy of the simulation. For example, accurately simulating the timing effects of a transient glitch might require a lower level, like gate level, while a functional fault, like a stuck register, might be adequately simulated at RTL.
So you define the fault models, the types of faults, and the specific fault sites where you inject them.
Yes, precisely. You compile a list of relevant fault models, the type of fault you want to simulate, like a stuck at 0, stuck at 1, a transient bit flip, perhaps an open circuit, or even more complex analog fault models. You define the exact fault sites, the specific locations, nodes, registers, memory cells, ports, where these faults will be injected within the design. This fault list can be huge, potentially covering millions of locations. Then you need a workload, which is the test environment or test bench that the circuit under test, the DUT, runs during the fault injection simulation. This workload is critical. It could be a comprehensive functional test suite that exercises all the chip's functions. Or, ideally, it should be a scenario that closely mimics the expected use case of the chip in the actual vehicle, running realistic software or stimuli. For instance, to verify a dual-core lockstep CPU, you'd use a basic workload that runs instructions and stimulates the CPU outputs to ensure the comparator correctly catches any mismatches when a fault is injected into just one of the cores.
And you can precisely control the injection itself, almost like playing God with the chip's internal workings during the simulation. Timing, location, duration.
Absolutely. Parameters like the type of fault, the duration of a transient fault, how long does the glitch last, the number of faults injected in a single simulation run, usually one, but sometimes multiple for specific analyses, and critically, the exact time and location of fault occurrence are all precisely controlled by the fault injection tool. This allows for a systematic and exhaustive exploration of the design's robustness under countless specific fault conditions, validating exactly how the safety mechanisms respond to particular threats.
What are the typical results you get from fault injection, and how does it help build confidence in the overall safety of a semiconductor design?
Fault injection results are fundamental for demonstrating safety. They're used to verify the safety concept and the underlying assumptions made during the architectural design phase. Did the safety mechanism behave as we thought it would? It provides concrete, often quantitative, evidence for the effectiveness of the safety mechanism. It confirms its actual diagnostic coverage by showing exactly which injected faults it successfully detected, which it missed, and which were maybe safe anyway. It also helps refine the estimate of the number of safe faults, those faults that occur but demonstrably don't violate safety goals under the simulated conditions.
And how do you judge the quality of the fault injection campaign itself?
The standard emphasizes that the confidence of the computation and verification with fault injection, how much you trust the results, is directly evaluated based on two key factors. First, the quality and completeness of the test bench or workload used during injection. This is often measured by its functional coverage metrics. Did the workload exercise all the relevant parts and modes of the design? You need to ensure that the simulation environment accurately represents real-world operation. And second, the completeness of the fault injection campaign itself. What percentage of the defined fault list or fault sites were actually simulated? Did you cover enough ground? This rigor, especially the coverage achieved, is directly tied to the automotive safety integrity level, ASIL, being targeted. Higher ASILs demand much more stringent and comprehensive fault injection campaigns to demonstrate, with very high confidence, that the safety mechanisms perform as intended under virtually all conceivable fault conditions. It's really about leaving no stone unturned in the verification process.
This brings us to a really fundamental principle of ISO 26262, building safety in from the very beginning, right from the start of development, not just trying to test it in at the end or bolt it on as an afterthought. Clause 11, the development lifecycle, emphasizes this. How does functional safety integrate throughout the entire semiconductor development process, from the initial concept all the way to the final silicon?
Yeah, that's absolutely central. ISO 26262 provides a holistic framework for functional safety that is intended to integrate all these safety-related activities seamlessly into a company's existing standard development framework. This isn't just about the design phase. It comprehensively covers the entire safety lifecycle, from the initial concept and development through manufacturing and production into the vehicle's operation, any necessary service or updates, and all the way to final decommissioning. It's designed to be a continuous end-to-end approach to managing safety, ensuring reliability and risk reduction from the product's conception to its ultimate disposal.
And a major part of building safety during development is avoiding those systematic faults we touched on earlier, isn't it? These are the errors in the design itself or in the processes or documentation rather than random physical failures. These can affect every single chip made from that flawed blueprint.
Yes, avoiding systematic faults is absolutely paramount because they represent fundamental flaws that, if they slip through, can affect every single chip produced from a flawed design or process, potentially leading to widespread issues. For digital components, typically designed using hardware description languages, HDLs like Verilog or VHDL, even though we're talking about hardware, some principles borrowed from rigorous software development, specifically from ISO 26262-6, are adapted.
Like what kind of principles?
For instance, using automatic verification of coding rules, much like static code analysis tools in software development that check for common programming errors or unsafe constructs, is applied to the HDL code to ensure it's written robustly, clearly, and consistently according to predefined safety standards. There's also a huge emphasis on extensive functional and structural coverage-driven verification to ensure that the verification process adequately exercises every part of the design logic, structural coverage, and all specified functionalities, functional coverage.
So applying software like rigor to hardware description language design, including maybe the use of formal methods.
Yes, exactly. Specific verification techniques for digital design include HDL simulation, where the hardware design is run in a sophisticated software environment to check its behavior against specifications using test benches. Then there's formal verification, which uses mathematical proof techniques to formally guarantee that certain properties of the design, like this state is never reachable, or this output always follows this input, will always hold true under all possible input conditions. It's like a rigorous mathematical proof in geometry, providing very high confidence for specific critical properties. We also use requirement-driven verification, ensuring every single safety requirement traced down to the hardware level is explicitly verified by one or more test cases. And of course, extensive pre-silicon verification, simulation, emulation, at both the module level for individual blocks and the top level for the fully integrated chip. To ensure inherent robustness in the design itself, design principles like restricted use of asynchronous constructs are often applied to avoid tricky timing anomalies that can be difficult to analyze and verify. And there's a conscious avoidance of not testable or poorly testable structures to ensure that engineers can achieve high test coverage for faults, both during production testing and potentially using in-operation self-tests.
And for analog and mixed signal components, which are designed quite differently, what specific measures are taken there to avoid systematic faults during their unique design process?
Right, for analog, the methods are different due to their continuous non-digital nature. It involves meticulous schematic entry, literally drawing the transistor-level circuit layout accurately. This is often followed by behavioral model simulation for critical analog blocks early on, using simplified models to test their general behavior and interaction before diving into detailed transistor simulation. Then rigorous corner simulations are absolutely essential.
Corner simulations? What's that?
This means simulating the circuit's behavior, not just at typical conditions, but also at the extreme edges or corners of expected manufacturing process variations, fast versus slow transistors, and environmental conditions, lowest highest voltage, lowest highest temperature. You have to ensure it works reliably across the entire specified operating cube. They also often perform Monte Carlo simulations for particularly sensitive analog blocks. This involves running hundreds or thousands of simulations where component parameters, like resistance or capacitance, are randomly varied within their statistical tolerance ranges, mimicking real manufacturing variations. It helps predict the yield and ensure robustness against statistical spread, like rolling dice repeatedly to see the distribution of outcomes.
So really trying to break the design under every conceivable variation before it even goes to silicon fabrication.
Precisely. Design for testability, DFT, is also key for analog, just as for digital. This might involve including specific hardware structures, like internal test points or dedicated test modes, to improve the controllability and observability of internal signals, enhancing test coverage during both development and production. And specialized schematic checkers are used automated tools that check the drawn circuit for common errors, like incorrect interconnections, proper device selection based on voltage ratings, and even sophisticated safe operating area SOA checkers to ensure transistors and other components are always operating within their specified safe limits and not being pushed beyond their capabilities, which could lead to premature failure.
What about programmable logic devices, PLDs or FPGAs? Are their design considerations unique, especially since their internal functionality is defined by configuration data, almost like loading software?
Yes, PLDs, being configurable, has specific considerations related to avoiding systematic faults in both the underlying hardware and the configuration process. There's a strong emphasis on structured description and modularization of the PLD functionality described in HDL, breaking down complex designs into manageable, independently verifiable blocks. It's also absolutely critical to carefully check and adhere to PLD vendor requirements and constraints during the various stages of the complex software tool flow synthesis, translating HDL to logic gates, mapping, assigning logic to specific PLD resources, placement, deciding where logic goes on the chip, and routing, connecting it all up. These highly specialized software tools define exactly how the logic is physically implemented on the chip fabric, and their specific rules, recommendations, and limitations must be followed precisely to ensure correct and reliable operation.
And the tools themselves need to be trusted, don't they? If the place and route tool has a bug, it could introduce systematic errors right into the hardware configuration.
Absolutely. That's a critical point. The reliability of the PLD design tools themselves, particularly complex ones like place and road engines, must be analyzed for confidence in use, according to the specific guidance in ISO26262 said Clause 11, Tool Qualification. A malfunction or bug in these tools could potentially introduce systematic errors into the final hardware configuration data, undermining safety. So engineers often need to perform rigorous tool evaluation, validation, or sometimes implement mitigating measures in their design process to ensure the tools they rely on are sufficiently trustworthy for a safety-critical application.
Okay, so once the individual components and blocks are designed and verified individually, how does hardware integration and verification work for semiconductors? How do you ensure all these tiny, complex pieces play nicely together when assembled into the final chip?
Right, integration is where it all comes together. The standard interprets the general hardware integration testing methods described in ISO 26262-5 and applies them specifically to the context of semiconductors. Test cases for integration testing are meticulously derived using various methods, including analysis of requirements, especially interface requirements between blocks, examining internal and external interfaces for potential issues, using techniques like equivalence classes and boundary values to thoroughly test ranges of data exchanged between blocks. They also use error guessing based on known design concerns or potential weaknesses in interfaces, analyze functional dependencies between blocks, test under common limit conditions like variations in shared clock speed, power supply noise, temperature gradients across the chip, or external EMI, simulate relevant environmental conditions like vibration effects, and ensure testing covers significant variance such as process, voltage, and temperature PVT combinations across the integrated chip.
So really pushing the limits of how the integrated chip might perform under every stress imaginable, focusing on those interactions between blocks. What are the actual testing approaches used during this integration phase?
The testing approaches typically include extensive functional testing, which is primarily performed in pre-silicon simulation or emulation environments where the entire integrated design is run with realistic stimuli. Then, once first silicon samples are available, electrical testing is done on physical prototypes using lab equipment to verify signal integrity, power consumption, and basic functionality. And crucially, fault injection testing is also applied here at the integrated level, as we discussed earlier. This verifies the effectiveness of safety mechanisms in the context of the fully integrated chip, ensuring faults don't propagate unexpectedly across block boundaries or interfere with other safety functions.
And just to be clear, this hardware integration verification is different from production testing, right? One is verifying the correctness of the integrated design, the other is verifying each manufactured piece.
Yes, that's a critical distinction the standard makes. Hardware integration verification focuses on confirming the correct integration of different pre-verified blocks and identifying any systematic faults introduced during integration or inherent in the design itself. It's primarily about proving the design works as intended when assembled. This verification is typically performed on a subset of devices, early prototypes, or engineering samples. Production testing, on the other hand, occurs much later in the product lifecycle, after the design is finalized and frozen. Its primary focus is on detecting random manufacturing faults, like stuck bits, opens, shorts caused by process variations, and ensuring conformance to specification. Production testing is applied rigorously to all produced devices, every single chip that rolls off the assembly line, to weed out defective units. The goal of hardware integration verification is proving the design is safe and correctly integrated, whereas production testing is proving each manufactured part conforms to that safe design and doesn't have any individual manufacturing defects.
So, safety isn't just a design consideration. It truly spans the entire product lifecycle. Let's talk about safety beyond the design phase now, particularly during production, operation, and even decommissioning, which is covered briefly in Clause 13. How do we ensure safety is maintained during the high-volume semiconductor production process itself?
Right, moving from a verified design to millions of safe parts is critical. During production, semiconductor products are fabricated through highly complex and standardized manufacturing processes in specialized factories called fabs. These processes typically have extensive risk mitigation in place through methods such as process FMEA, that's failure mode and effects analysis, applied to the manufacturing process steps themselves, and comprehensive control plans.
So, analyzing what could go wrong during manufacturing.
Exactly. It means every step of manufacturing, from raw wafer fabrication through etching, deposition, lithography, all the way to dicing the wafer into individual chips and packaging them, is meticulously monitored and controlled to minimize the chance of introducing defects that could impact functional safety later on. Statistical process control, SPC, is used extensively.
And this is where every single chip gets tested, not just a few samples like in design verification, that massive scale production testing.
Exactly. This is where production testing comes into play, performed on automated test equipment, 8E. As the standard notes, state-of-the-art production testing applies structural tests to every single chip produced, often at different temperatures. These structural tests, like scan testing, memory BS, are designed to efficiently detect common manufacturing defects. This step is absolutely critical for weeding out those inevitable random manufacturing defects and ensuring that what was designed safely is also built safely, without flaws introduced during fabrication. If a chip doesn't pass these rigorous production tests, it's discarded. It doesn't leave the factory.
Are there also specific measures taken during or after production to detect and weed out early failures, those components that might pass the initial quick tests but are perhaps weak and destined to fail prematurely once they're out in the field? The infant mortality part of the bathtub curve.
Yes, absolutely.
Yeah.
Especially for safety-critical components, additional measures are often taken specifically to detect and weed out early failures and assure the long-term robustness of the manufactured chip. A common example, as you mentioned earlier in a different context, is burn-in. Here, batches of chips are operated, sometimes under stress conditions like high temperatures and elevated voltages, for a period, maybe hours or even days.
Why do that?
The idea is to accelerate any inherent weaknesses or marginal defects in the silicon that might have barely passed initial testing and make them fail early, under controlled conditions in the factory, before they ever reach the customer or get integrated into a vehicle. This ensures that the chips that do survive this accelerated aging process are likely to be the truly robust ones from the manufactured population. Similar stress tests, like high voltage stress, might also be applied. For sensors specifically, techniques like optical pattern inspection of critical MEMS layers during manufacturing can be used to detect tiny physical anomalies and call potential early failures that could lead to safety issues later. It's like a rigorous stress test or screening before final deployment.
So literally baking in reliability and robustness by stressing them first. Okay, what about safety during a vehicle's operation and service life? How do we monitor semiconductor-related faults once these chips are out in the field driving around for years?
Right, safety doesn't stop when the car leaves the factory. During the vehicle's operation, there's ideally a continuous need to monitor semiconductor-related faults using the built-in safety mechanisms and diagnostics we discussed earlier. And crucially, there should be a process to gather field incident data. This feedback, understanding what's actually failing in real-world conditions, maybe thousands of miles into a vehicle's life, is invaluable.
Why is that feedback so important?
Because it helps refine our understanding of real-world failure rates, identifies potential systemic issues that might have been missed, and allows for continuous improvement in future designs, manufacturing processes, or even software updates for existing vehicles. It's meant to be a closed-loop system of continuous learning and improvement for safety.
But I imagine getting good, specific field data back down to the level of an individual semiconductor component can be really tricky, right? Especially when they're embedded deep within complex electronic modules.
It definitely can be. The standard acknowledges that implementing an effective field monitoring program for semiconductors can be challenging due to the typically limited field feedback that often reaches the original chip designer. Information might get lost as it goes through the system supplier, Tier 1, and the vehicle manufacturer, OEM. Also, complex intellectual property, IP blocks within a chip, might be configured differently in various systems, making direct comparisons difficult.
So it's a known challenge.
It is. However, many of the on-chip safety mechanisms we talked about, like ECC correcting memory errors, thermal monitors detecting overheating, voltage monitors flagging power issues, or various periodic self-tests, like memory biased or logic biased, run during operation, are active precisely to detect faults as they occur in the field. They provide real-time operational safety and often log diagnostic trouble codes, DTCs, that can be retrieved by technicians during service, providing some level of field monitoring, even if perfect feedback isn't always possible.
And finally, a brief mention of decommissioning considerations. This seems like the very end of the line for the chip and the car. What does functional safety have to say about that?
It's mentioned as part of the overall safety lifecycle. While Part 11 doesn't delve into extensive detail on specific decommissioning procedures for semiconductors themselves, the principle is that functional safety considerations do extend to the decommissioning phase of the product lifecycle.
Meaning?
This generally implies ensuring safe disposal or proper management of end-of-life electronic components and systems. Given the materials involved in semiconductors and electronics and the potential, though perhaps low, for remaining electrical or chemical hazards, it's about ensuring the entire life cycle, from design conception to final discard, is handled responsibly and safely, preventing harm to people or the environment even at the very end.
So pulling all of this incredibly detailed information together now, what's the bottom line? What's ISO26262 Part 11's indispensable role in the grand scheme of automotive functional safety? Why does all this intricate detail from microscopic chips matter so much for the car you drive every day?
Well, I think Part 11 fills a truly critical gap. By providing its informative character only, meaning it offers guidance and interpretation rather than strict rules, but offering those crucial possible interpretations of other parts of ISO 26262 with respect to semiconductor development, it ensures that the smallest, most fundamental building blocks of all the complex EE systems, the semiconductors, are developed and managed with the same rigorous functional safety principles as the larger systems they enable.
So it connects the big picture safety goals down to the tiny detail.
Exactly. Without this specific guidance for silicon, the entire safety chain could potentially be compromised at its weakest, most fundamental link. You could have a perfectly designed system architecture, but if the underlying chips aren't developed with the same safety rigor, the whole thing could fail.
It's not just an afterthought, then, bolted on at the system level, but safety truly ingrained right down at the deepest level of the hardware.
Absolutely. The holistic view is paramount here. Our detailed understanding and meticulous management of faults, errors, and failure modes at the semiconductor level, as covered in our discussion on Clause 6, directly informs and enables all the higher-level system safety analyses. If you understand the potential failure modes of the silicon building blocks, you can better predict, mitigate, and control the potential failures of the entire electronic system built from them.
Right.
The quantitative analysis, using base failure rates and the calculation of hardware architectural metrics like SPF, LFM, and PMHF, guided by Clause 7, provide crucial, measurable data. This data feeds upwards into the overall system safety case, allowing engineers to demonstrate that the hardware contributes acceptably low risk and meets the overall safety targets for the vehicle function.
And the analysis tools we talked about, like FMETA and especially that qualitative detective work of DFA, are critical at this low level too, right? It sounds like they uncover hidden risks that you wouldn't see otherwise.
They absolutely are. Performing FMETA, and especially the crucial dependent failure analysis, DFA, right down at the chip level, as guided by Clause 9, is essential. They help reveal potential hidden risks, those subtle common cause failures or unexpected cascading effects between supposedly independent circuits that could otherwise compromise overall system safety, even if individual components or safety mechanisms seem robust when analyzed in isolation. And then fault injection testing, covered in Clause 10, provides that invaluable empirical evidence. It really bridges the gap between theoretical safety models and real-world hardware behavior, demonstrating that the safety mechanisms actually work as intended under simulated fault conditions, proving their effectiveness in a way analysis alone sometimes can't.
And building safety in from the ground up during development, right from the very first line of HDL code or the initial circuit diagram, that systematic avoidance.
Precisely. The focus on systematic fault avoidance measures, like coding rules, robust design principles, verification methods, and rigorous hardware integration and verification activities, all detailed in Clause 11 and embedded throughout the entire semiconductor development lifecycle, ensure that safety isn't an add-on, but is engineered in from the very foundation of the silicon. And then finally, the considerations for production, operation, and decommissioning discussed in Clause 13 extend that safety umbrella throughout the product's entire life, meaning functional safety is considered from the silicon's birth all the way to its final retirement.
So it really is a seamless, unbroken chain of safety considerations, from the microscopic transistor design all the way up to the macroscopic vehicle function and ensuring the safety of its driver and passengers. It's truly an invisible guardian working deep inside our cars.
Indeed. By providing these unique, specialized guidelines tailored for the semiconductor world, Part 11 ensures that functional safety is not just an afterthought or a high-level system concern, but is deeply ingrained in the very silicon itself. This meticulous, multi-layered approach makes automotive electronic systems inherently more robust and reliable, which is essential as they become ever more complex and take on more safety-critical roles. Ultimately, it ensures that these lowest-level components, the semiconductors, truly and reliably support the entire system's safe operation.
You know, what truly stands out for me from this deep dive into ISO26262 Part 11 isn't just the sheer technical complexity, which is obviously immense, but it's the incredible meticulousness and foresight required to engineer safety into our vehicles at this fundamental level.
Yeah, the level of detail is pretty staggering when you think about it.
It really is. It's a profound reminder that the safety we often take for granted when we're just driving down the road isn't magic. It's meticulously engineered, bit by bit, transistor by transistor, by incredibly dedicated teams of engineers working to tolerances and complexities that are almost hard to fathom. It truly makes you appreciate the unseen work that goes into every single drive you take.
It's definitely an invisible guardian, constantly at work under the hood, so to speak.
If you, our listeners, are interested in maybe exploring how this applies to specific types of components within your vehicle, maybe sensors versus processors, or perhaps the fascinating interplay between hardware safety mechanisms and software diagnostics in achieving overall functional safety, do let us know. There's always more to unpack in the incredibly complex and absolutely vital world of functional safety.